Today we are going to discuss about the electricity and magnetism. That means magnetic effect of current and vice versa also. Now, electricity and magnetism both have been known for more than 2000 years, but there is a relation between the two was not discovered. Only about 200 years ago it was realized that they are intimately related. They are means electricity and magnetism are intimately related. First, by an experiment, it was shown by Hans Christian Oersted. Hans Christian Oersted, a Danish physicist, observed that the magnetic effect of current in 1820. He performed simple experiments with a straight current carrying conductor and a magnetic needle, and his observations are as follows. What he have done, he took a magnetic needle and also a current carrying straight conductor. When current allowed to flow through a wire placed along the axis of a magnetic needle kept directly below or above, whatever, and close to the wire, the needle was found to deflect from its original position. That means, if let us say this is a magnetic needle, right? This is a magnetic needle whose north side is this, north pole is this, and south pole is this. Now, if we place a conductor, just above the magnetic needle, and the wire is also parallel to the axis of the needle, right? Now, if current flows in this direction, current carrying conductor is above the magnetic needle. Magnetic needle's north pole is this and south pole is this, and current is flowing through this direction. Then if current flows this direction, then the magnetic needle will deflect in this direction. This is shown by Oersted. Now if current stops the current, we stop the current, then magnetic needle will remain or regain its original position. That is, it is north pole pointing towards the north. Now, Oersted reverses the current. That means this is north pole, this is south pole. Now, current is flowing through this direction. Then it was seen that north pole is deflected towards this direction. Is it clear? If we stop the current, then again magnetic needle will regain its original position. Now, if we place the current carrying conductor just below the magnetic needle, and current is flowing through this direction, then magnetic needle will deflect along this direction. Right? Stops the current against original position. Again, we place the current carrying conductor below the magnetic needle, and current is passing or flowing through this direction to this direction. Then magnetic needle will deflect in this direction. If the current carrying conductor placed in perpendicular direction, in normal to the magnetic needle, whether it is above the needle or below the needle, there is no deflection in the magnetic needle. If we increase the intensity of the current, then also magnet deflect and amount of deflection will be greater. If you increase the current, then amount of deflection will be greater. Now, these are the observations of the Oersted experiment. Very simple experiment. Anyone can perform the experiment. This is a magnetic needle. This is N side, this is S side. If we place a current carrying conductor, current is flowing this side to this side, just above the magnetic needle, then it will deflect along this direction. If current is along this direction, then this north pole will be deflecting in this direction. If we place below the magnetic needle, then above it will into the board, now out of the board. Clear? All these things are clear. That means we are going to say that the deflection of the needle was found to be in opposite direction. If we reverse the current direction, or if we reverse the position, that means reverse means if above current carrying conductor is above the magnetic needle, then reverse means it will be placed in the below the magnetic needle. That means we want to say that the deflection of the needle was found to be in opposite direction. On reversing the direction of the current, or if we reverse the position, keeping the direction of the current same. Right? These are the observations. And third observance is what? The magnetic needle will remain unaltered. That means it will not deflect if the current carrying conductor is placed perpendicular to the magnetic needle. That means perpendicular to the axis of the magnetic needle. If we increase the intensity of the current or magnitude of the current, then deflection will increase. Right? These are the observations. These observations led Oersted to interpret that there must be some magnetic effect around the current carrying conductor, which deflects the magnetic needle. Right? We know that if here is a magnet, then if we place another magnet, then that magnet will experience a force. Like that means we know that magnet experiences a force if there is a magnetic field. Right? Now, we do not place here a magnetic field, but just we place here and current carrying conductor and magnetic needle is deflecting. Then from here Oersted infer that current carrying conductor must have magnetic fields. From here, from this experiment, we can say there is a relation between electricity and magnetism. Here magnetic field produced by current, and current means electricity. Current means flow of charge. That means from electricity we produce a magnetic field. Now he concluded that an electric current or charge in motion, current means charge in motion, produces magnetic effect in surrounding space. Thus, flow of electric charge or moving charge is the source of magnetic field. We know that source of electric field is charge. What is the source of gravitational field? It's mass. Similarly, source of electric field is charge, and source of magnetic field is moving charge. That is current, or we can say that is current element. We are going to discuss later. Now, Maxwell, Hertz, Bose, Marconi, these scientists have further worked on the findings of the Oersted's experiment. They carried out many experiments and proved that laws of electricity and laws of magnetism are interconnected, are unified. Direction of deflection of magnetic needle. Now, we just set the observations, told the observations of the experiment. That means current flows this direction and magnetic needle deflect in this direction, current through this direction, magnetic deflection in this direction. Now, which direction magnetic needle will deflect? This is given by a law that is called the Ampere's swimming rule. Direction of deflection of magnetic needle due to electric current can be found by applying Ampere's swimming rule. And what is the swimming rule? Swimming rule is like that. Imagine a man swims along the direction of the current. A man swims along the direction of current facing the magnetic needle. He swims along the magnetic in such a way that he can see the magnetic needle. Then north pole of the needle deflects towards his left hand. See here. Just this is magnetic needle, this is north pole, and this is the magnetic current carrying conductor. And current flows this direction. Now, if I am the swimmer, then I have to swim in this direction and face. That face should be in this direction. Then I have to like this, my left hand towards this. That means north pole of the magnetic needle deflect along this direction. Now, if this is placed below the magnetic needle, then if I swim like this, then I cannot see the magnetic needle. I have to swim along like this, reverse. Then my left hand goes in this direction. That means magnetic needle will deflect along this direction. I think you have understand the Ampere's swimming rule, and you can apply also in the different cases to find the magnetic field. That means deflection of the north pole of the magnetic needle due to an electric current. Now, this is the first observation or first experiment done by Oersted, by which we can say that magnetic field is due to an electric current, and which is called the magnetic effect of current. Now, what is magnetic field? We have already told electric field, gravitational field. Gravitational field is the a region surrounding a mass in which another mass experiences a force. Like that, a region surrounding a charge in which another charge experiences a force is called the electric field of the first charge. Similarly, the space or region surrounding or around space or region around the current carrying conductor within which its influence can be felt by what? By a magnetic needle is called the magnetic field of the current carrying conductor. That means if this is a current carrying conductor, then around the current carrying conductor, if we place a magnetic needle and it will experience a force, then that region is called the magnetic field of this current carrying conductor. Now, strength of the magnetic field denoted by B vector. Strength of the magnetic field due to a current carrying conductor is denoted by B, and often it is called the magnetic flux density. This is also called magnetic flux density, or it is also called magnetic induction. It is also called magnetic vector, or you can simply say magnetic field. Also it is called magnetic field. Though we know that magnetic field is a region, yet we can say that strength of the magnetic field is called only magnetic field. right? Now SI unit of this B magnetic field is Tesla, denoted by capital T, and Cbse unit is Gauss, denoted by G, and 1 Tesla is equal to 10 to the power 4 G. In the later discussion, we will define 1 Tesla. Some properties of magnetic field B. Magnetic field B is a vector quantity. That means it has both magnitude and direction. It can be time dependent. That means it can change its time. B depends upon the permeability of the medium. More than one magnetic field can be added vectorally to give the resultant magnetic field. That means magnetic field obey superposition principle. As we have told in the electric field discussion, superposition principle, electric field also obey the superposition. Like that, magnetic field also obey the superposition principle. And mind it, magnetic field is a vector quantity. That means it has a magnitude as well as it has a direction also. Now, like the electric field vector, it is like that the force between two electric charge is along the line joining, but here fields due to a current carrying conductor, that means current carrying conductor is a vector quantity, particular direction it has a direction, and the radius vector, that means distance vector of the field point from the current carrying conductor is also a vector quantity, and due to the current carrying conductor there is a magnetic field, that is also a vector quantity. Now these three vectors may be in different plane. That's why if the magnetic field is not on the plane of the board, then you have how you can denote that vector, or how you can specify that vector in a copy or in a board. In that case, we have a convention. The magnetic field perpendicular to the plane of paper or plane of board in the upward direction. That means if magnetic field is out of the board or out of the paper, then it will be denoted by this sign. This sign means that magnetic field is perpendicularly out of the board, and the magnetic field to the plane in the downward direction or into the board. If the magnetic field is perpendicularly into the board or into the paper, then it will be denoted by a cross. This means perpendicularly into the board, magnetic field vector, and this means perpendicularly out of the board. If we draw in a board, then this is the convention. If we draw this in a copy, then that can be written as perpendicularly out of the paper or perpendicularly into the paper. We take a straight current carrying conductor and it is passed through a cardboard. Like say this is a cardboard and a straight current carrying conductor just perpendicularly to this cardboard, and we place some iron filings in this cardboard. Now if we vibrate or just vibrating this small vibration in this cardboard, then we can see that iron filings are arranged themselves in concentric circles around the wire. If this is the wire, then iron filings will be arranged themselves in these circles, keeping the wire at the center, or the center of the concentric circles are at the wire. Again, if a magnetic needle is allowed to trace its path around the conductor, once again we found that it is circular. That means the path in which the magnetic needle trace will be circular path. Thus, the magnetic field around a current carrying straight conductor consists of concentric circles of magnetic field lines lying in a plane which is normal to the current carrying conductor. That means if this is a current carrying conductor and this is the cardboard, then iron filings will be like this. These are on the plane perpendicular to the wire. These circles are, right? And these lines are called the magnetic field lines. The magnetic field lines are crowded near the conductor, and which shows that intensity of the magnetic field is greater near the conductor and further apart at a distance from the conductor. As the distance from the conductor increases, these lines will be further apart, which shows that intensity of the magnetic field decreases as the distance from the conductor increases. Right? Just we are going to just make an analysis or qualitative discussion of the magnetic field. That means if this is a current carrying conductor, then this due to this current there will be a magnetic field, and magnetic field lines are concentric circles, and these circles are dense or very close to each other when the distance is smaller, and when distance is larger, these circles are further apart. Further apart means in that region electric field intensity decreases or very small, and not electric field, magnetic field intensity. In the further distance, or if the distance of the field point from the conductor increases, then magnetic field decreases, and at the near point, that means very close to the conductor, magnetic field intensity is larger or greater. And also, since magnetic field has also direction, then this field lines also have directions, and from which we get these directions. There are many rules to get the direction of magnetic field at any point, and it will be also the magnetic field, the direction of the magnetic field at any point is along the tangent to the magnetic field line. That means if this is the field line, then tangent means into the. Since in this position means if current carrying conductor is on the board, then in this point the current magnetic field is into the board. Clear? And this direction of magnetic field lines or direction of magnetic field, we get it from many rules. I just state only two rules. One is right-handed screw rule. Right-handed screw rule, or it is also said Maxwell's quart screw rule. Maxwell's quart screw. If the forward motion of an imaginary right-handed screw, forward motion of an imaginary right-handed screw is in the direction of the current, through the linear conductor, then the direction of rotation of screw gives the direction of the magnetic field at that point. That means if current is flowing through this direction, then you have to rotate the screw like this so that it can advances along a direction to the direction of current. Second rule is called the thumb rule. Rather, it is called right hand thumb rule. What is the rule? Rule is, if a conductor carrying current is imagined to be held in the right hand such that we are just take this current carrying conductor in my right hand, then such that the thumb points in the direction of the current is flowing through this direction, then I have to hold this like this. This is the thumb, gives the direction of the current. Then the direction of the encircling finger, the fingers which encircling the current carrying conductor, the direction of the fingers, curling fingers, gives the direction of magnetic field line. We have just discussed that there is a magnetic field if there is a current. If I have a current carrying conductor, then there will be a magnetic field surrounding or around that conductor, and that magnetic field is larger when the distance is small, and that magnetic field will be smaller if distance is large. And also we get the direction from the Maxwell's corkscrew rule, and also we may get it from the right hand thumb rule.